Yay!
Yay! Okay, a long time ago when we were doing masses on inclined planes and using Newton's laws to find out the acceleration of the system, maybe they're tied together by pulleys and ropes and whatnot. What we did is we always had the pulleys be massless. And we just said they're easy to spin and they're massless. And that made the problem a lot easier because all the tensions were the same. This time, though, we're not going to be able to get away with that. So now that we know how to handle rotating things, let's say that I've got two masses that are tied together over a pulley. But now, let's have that pulley be a solid disk, and it's massive. It's a massive disk. So it takes some force to spin that thing. So now we're going to say that pulley has a mass of 10 kilograms, like I've got up here. There's the pulley. So it's got a mass of 10 kilograms, a radius of 25 centimeters. Let's see what the acceleration of this system is now, taking into account that massive pulley. Okay, here's how we do it. There's just an extra step. We have to include Newton's laws for the rotation of the pulley alongside the masses. Okay, so we're going to set it up in almost the same way that we used to. So here's what we used to do. We said, let's set up Newton's laws for M1. So for M1, oh, by the way, let's say that there's friction on this thing. So the friction for both M1 and M2 I've got is like 0.36. Okay, so let's set up Newton's laws for M1. So for M1, I'm going to have tension pointing to the right. So that's going to be, now, it's not going to be true anymore that the tension all along that rope from M1 to M2 is going to be the same because that pulley is going to spin. So we're going to figure it out later, but those two tensions can't be the same because there has to be a net force, a net torque on that pulley to make it spin, right? So those tensions can't be the same anymore. So I'm going to have to call them different things. So I'm going to have T1 pointing to the right. The friction on M1, we'll kind of go quickly past this because we've done it before, right? You're pros. So T1 minus mu M1G, mu times the normal force on M1. This is going to be equal to, let's say, we know this thing is going to be accelerating to the right, if M2 is more massive. So this is going to be M1 times A. Okay, cool. How about for M2? For M2, let's see, what I'm going to have is I've got the force of gravity pulling the thing down the plane. So that's going to be M2G sine theta, right? Remember, that's the force of gravity pulling something down the plane. Tension is going to be acting back up the plane, but I better call this T2. And then also there's friction minus mu times the normal force. The normal force of a mass on the plane was mu. The normal force is M2G cosine theta. Remember, the normal force had the cosine theta. All right, and so this is going to be equal to M2 times A. It's got to be the same acceleration as M1, right? If we don't allow the ropes to stretch, that's going to be true. All right. Oh, and so now, how am I going to, because I have T1 and T2, how do I tie them together? I get these things to be related to each other through the torque on the pulley. Okay, so the pulley, it's rotating, right? So I better use the rotational form of Newton's second law. So the sum of the torques, it's a vector, but we'll just indicate it with the direction, equals I times alpha. Okay, as this thing is moving, remember the connection between alpha and A. If it's not slipping, alpha is just A divided by R, right? So what are the sum of the torques? Well, I've got T2 is pulling it to the right, and T1 is trying to pull it to the left. How did I indicate it here? It looks like I have minus T1 times R plus T2 times R, because both of those tensions are acting perpendicular to R tangent to the circle, right? Tangent to the pulley. And that's the sum of the torques. They're acting r away from the center of rotation. This is a solid disk, so this is going to be 1/2 times mr squared. And then I've got A divided by r, right? Well, if I look at this, this is going to simplify quite a bit because on the left-hand side, I can factor out an r, put it over on the right-hand side, and then all the r's cancel. So that's nice. So those r's can combine with that r to cancel the r squared. That's cool. So I have a much simpler equation that is just T2 minus T1 is equal to 1/2 ma. There we go. So everything is in terms of a's. So it looks like I can just start substituting things in, and then I should be all right. So let's see what I did first. Let's look at T2. Let's take T2, substitute that in there, and then I'll take T1, substitute it in there, and then we should be able to solve for A. Everything's in terms of A in that case. All right, so let's do it. So T2, what is T2? T2 is m2g sine theta minus mu m2g cosine theta, and then I'm going to have a minus m2a. There, that's T2. And then I'm going to have a minus T1. Okay, minus, what the heck is T1? T1 is m1a plus mu m1g from the first equation. And this is going to be equal to 1/2 ma. Okay, so now I can just gather all my A terms together. There's 2 of them on the left-hand side, so I can just add them over to the right-hand side. So it looks like what I've got is, let me factor this out, m2g sine theta minus mu cosine theta. The A term is going over to the right-hand side, right? So I don't need to worry about that. And then I'm going to have a minus mu m1g. And then on the right-hand side, I'm going to have an A. And then factoring that out, I get a 1/2 m plus m1 plus m2. And then I divide it over on the left. All right, so if I plug all that stuff in, there's some tedious calculation there, but I know the angles, I know m1 and m2. So if I plug all that stuff in, A, what did I get? A is going to be 0.31 meters per second squared. Cool. So that's the acceleration of the system. And then you can go back and verify. Remember we said in order for that thing to turn, those 2 tensions are not equal to each other. You can go back and figure out T1. If you plug these numbers back in, T1 is going to be 7.68 Newton meters. And T2, what did I get for T2? 9.22. And I just wanted to illustrate that it's true in this case. In order to get that thing to spin, it must be that the tension on the right-hand side is greater than the tension on the left-hand side, because you need that unbalanced torque to get the thing to spin. So that kind of makes total sense. All right, so this is how you combine pulleys and wheels tied together with ropes and combined with objects on inclined planes. So this is kind of a common sort of a problem that pops up when talking about rotational dynamics.